Okay, lesson 50. Here we try to go. Maybe. I don't know. Whew. Okay, lesson 50. Derivatives of composite functions, derivatives of products, and quotients of composite functions. So it's all about derivatives of composite functions. In all honesty, this is going to resemble a lot like chain rule. Okay, it's kind of another version of looking at it, another way to think about it, understand it, grab what you need to grab. You're fine. But all in all, I feel like you guys will have an idea of what we're doing. It's putting things like chain rule, product rule, quotient rule together more. Okay, so as we look at our first example here, derivatives of composite functions. When we first start off with this, we talked a little bit about U substitution, and that's what we're going to start off with today. When we have something like e to the 2x, what's the base function there that you'd be taking the derivative of? Okay, e to 2x, e to some power, right? Okay, e to the x, whatever. So what I'm going to think of this as for a moment is the idea of U substitution. So I'm going to say, okay, I'm going to represent my function as y equals e to the u. And if I do that, what is u? U is representing 2x. Now, we can take our derivatives using differentials. So we've done stuff like this before. I am going to use the differentials instead of like the dy and dy over du. Just when I say differentials, derivative of y term, I tack on a dy. Derivative of u term, I tack on a du. Same thing with x's. So here, the derivative of y equals e to the u. So derivative of y, I would represent as dy, because the derivative of y is 1, and then dy. Derivative of e to the u. E to the u, du officially, yes? Okay. Let's do the same thing with our u equals 2 to the x. Derivative of u, du. Derivative of 2x. 2, and then dx. Now, since our original problem was in terms of y and x, we want our final answer to be in terms of y and x. And so right here, if you look at dy equals e to the u du, do we know what u is? Yeah, u is 2x. We can substitute the u back in. Do we know what du is? Didn't we just find du to be 2x? 2dx, excuse me. So we can substitute these values back in. So dy equals e to the, what am I using for u? 2x times du, which what was du? 2dx. Clean this up a little bit, since we are trying to find the derivative. We're trying to find dy over what? Dx. So if we clean this up, divide the dx over to be with the dy. dy dx is going to equal what? Okay. 2e to the 2x would be our most cleaned up version. Okay. When you have that 2, we generally like to put it out front. Now, U substitution is helpful. Is it required? And my answer would be no here. Okay. And honestly, a lot of this page, I'm not going to necessarily use this U substitution unless we, I might by the time we get to the last one, just, make sure things make sense. But I wouldn't necessarily use U substitution as a general rule. unless it's an extremely complicated problem. But the idea here, if we do the derivative of e to the 2x, the derivative of e to some power is e to some power times what? The derivative of that power. And the derivative of 2x is the 2. And so thus we have 2e to the 2x. Now, if you like the u substitution better and that makes it clearer for you, then that's an option as well. Okay? It's just, in my view, it's just varying levels of understanding. The more ways we look at it, the better the understanding is out there for you guys, I feel like. So, okay, questions before we try the next one? Okay, let's look at example 1 then. If f of x equals sine of 2x squared plus 4x plus 6, what is f prime of x? Do you guys want me to go do the u substitution again, or do you just want me to do traditional chain rule that we've kind of already worked with? You guys okay with chain rule? I'm getting some not convincing responses one way or the other, but okay. Well, we'll try it that way. So derivative of f of x is f prime of x, as always. Okay. Derivative of sine of something. Cosine of something, which means what? We write cosine and then we keep the something. So I'm going to keep the 2x squared plus 4x plus 6. And then what do I do? Okay. Times the derivative of what I called something. Daryl said the derivative of the inside. So what is the derivative of 2x squared plus 4x plus 6? Okay, derivative of 2x squared is 4x, plus derivative of 4x is 4, plus derivative of 6 is 0, non-existent. Okay. In terms of cleanup on this one, not really a cleanup, is there? Okay. You could possibly write your answer like this, or to be honest, what I would suggest is taking the 4x plus 4 and putting it out front. Okay, so the idea, it still has to be in parentheses, but 4x plus 4 times cosine of 2x squared plus 4x plus 6. Because then there is no question about, is that 4x plus 4 inside the cosine function, or is it just multiplied by the cosine function? If we put it beforehand, we know it is before the cosine function. So that, to me, would be the ideal way to write it. However, the other one's not wrong. Okay. If we had done u substitution, what would we have used u for? Yeah, we would have had sine of u and then gone from there. Okay? Are you okay with what I just did there? I mean, it's similar to what we've been doing, isn't it? We just have we've done the smaller stuff with chain rule. We haven't done the big stuff. So, okay, let's try example 2. Let g of x equals natural log of sine x and find g prime of x. Okay, we have g of x, g prime of x. What are your thoughts here to get us started? What? Okay, 1 over sine x. Because we're doing the derivative of, what's my main function here? Natural log, right? So it's natural log of something. And when we do the derivative of natural log of something, it is 1 over something. And my something is sine x. Am I done? No? Yeah. Unless your something is just x, you have to take the derivative of that something. And the derivative of sine x is cosine x. So I have 1 over sine x times cosine x. Am I done? Is there worthy cleanup here?
Yeah.
Well, we can make this a fraction, yes. 1 over sine x times cosine x over 1 makes this cosine x over sine x. One fraction would be cleaner than two things multiplied together. Yeah, cosine x divided by sine x is cotangent x. So final answer I would say here is cotangent x. Okay, that's one of those that you could memorize the derivative of the natural log of sine x. You will see that listed some places of something to memorize. However, to me, this is one that's very easy to figure out. There's not a ton of work there. Okay. Example 3. H of x equals x squared plus 4x to the 100th. Find h prime of x. Thoughts on this one?
Multiply the thing from parentheses by 100, and then keep the parentheses and subtract 1 from the next one.
Okay. So he's saying multiply by 100 in front, subtract 1 from that exponent. And maybe it will help you think here, but side note, we're doing the derivative of something to the 100th, right? And so if you need it, I can think of it as u to the 100th, right? So what's the derivative? Whoops, off the screen over here. The derivative of u to the 100th is 100u to the 99. But what is in our place of u? And that's that lovely x squared plus 4x, right? So that's where we're going to start off. H prime of x, the derivative of something to the 100th. So 100 times the something, I'm going to keep it the same, and then to the 99th, so subtract 1. Then what? Okay, times the derivative of x squared plus 4x. Derivative of x squared plus 4x is 2x plus 4. Okay. Ways to leave this problem. I mean, in all technicality, you could leave it as is. Okay, there's, nothing wrong with leaving it as is. A couple of things I want to point out, though. What do you recognize about 2x plus 4? There's a GCF of 2. So one option, yes, we can move it out front, but another option, if you take a GCF out of 2, then that becomes 2 times x plus 2, yes? What can that 2 multiply with? The 100. So one option of how to write this, is if we take the 2 times 100, that makes it 200. I'm going to go ahead and then put the x plus 2, and then make my x squared plus 4x to the 99th my last term. That's one option, and that is probably a more traditional option of what you might see. I have one other option, though. And we took a GCF out of 2x plus 4, yes. It was a 2, we multiplied it by the 100. What do you notice about my other parentheses? Okay, so there's a GCF of x, except when we take a GCF of x out of here, and these parentheses are raised to the 99th power, that means that x that I pull out is going to be an x to the 99th. We don't think of factoring like that very much, but that is another option, is that you can take that x to the 99th, since there's a GCF of x here, I would put it up with the 200 then. So then I have 200 x to the 99th, still times x plus 2, and now my x squared plus 4 instead is x plus 4 to the 99th.
How come we didn't pull out a GCF of 4 and a GCF of 1?
Because I didn't. I don't have a better answer to have. So the question was, why did I not pull out a GCF of 4 in the first one up here? And we could have pulled out a GCF of 4. You would have had 4 times x plus 1 times cosine of this. For the record, though, you cannot pull a GCF, or can you? I don't think you can pull a GCF from within the cosine. It would have to stay within it. But yes, we could have definitely pulled this 4 out and put it as 4x plus 1. I just didn't think about it at the time. I mean, to be honest, I just didn't think about it. Okay, are we good here? Because now we're going to continue working with these composite functions. So essentially we're working with chain rule. But we're also going to throw in product and quotient rule. So it's, we're kind of hitting those big bad derivatives where you've got rules within rules that you're trying to keep track of. So, as we look at example 4, f of x equals e to the x times x squared plus 1 to the 100th. And what is f prime of x? Okay, you got enough craziness going on there for you?